Okay, so here we go again. So I was asked where the videos are on the website, right? So first of all, if you go to the course website and you click on, systems or statistics, or at some point data streams, you will find a lot of related reading material, and you will also find there the videos, which unfortunately at the moment, thanks to some bugs in the transcoding at the Google side, don't have audio after 5 minutes or so. I'm sorry, I just could stand watching myself for 3-4 minutes, so I didn't notice it. But somebody told me that yes, after 5 minutes the sound goes away. I'll try and see what I can do to fix this. I filed a bug report and I'll try encoding it differently. But that's where the videos are. So if you like still movies, right now this is your place to go. Good. Now we're going to do data streams, and this is going to be probably a little bit less standard, and I think it should be new for pretty much everybody here in the room, unless they took a data streams and sketches class. Okay, so here's what we might want to do. So the first thing that I'm going to do is I'm going to tell you a little bit why on earth you care about data streams. Then we'll look at things like moment statistics, like Flageolet-Martin and Alon-Matthias-Szegedy sketches. There are better algorithms than Flageolet-Martin by now, but Flageolet-Martin is very simple, so that's why I'm going to explain it. Then I'll talk about heavy hitter detection, so lossy counting, space saving. These are, again, very simple algorithms. And a fair part of this class this time is going to be actually to prove that these algorithms do something useful. Then for, well, what I would call simmering statistics, because basically the update operations are essentially in a simmering, I'll get either the Bloom filter or the count-win sketch. And then finally, we'll look at things like real-time analytics, and in other words, how can we take a real data stream, parallelize things, so that's where the tools from systems will come from again, and actually have a mechanism to have very scalable statistics of the data, not just right now, but also historical data. So rather than, let's say, doing a Hadoop job, you will get through that estimates that are perfectly real-time, fairly accurate, and perfectly scalable and fault-tolerant. So we will probably not get to all of this at the end of this class today, but we'll do it next week. So let's start with what you might actually want to do with streams. So the key tenet of data streams is that, well, you usually can't go and replay the data. Or maybe you can replay it once if you put it in a buffer or something like that. The second thing is, you may only have a limited amount of memory or computers, and you really want to get real-time answers. So it's not okay to say, well, I'm going to fire up my Hadoop, Hive, or whatever instance and get the numbers back. And I might have, time series where I observe instances with a timestamp. In some cases, I might not do that. So for instance, for stock symbols, I clearly have timestamps, and these are essentially trade volume and scores and, whatever you might have. You might have video, you might have server logs. In these cases, the timestamps actually matter. And so there you might want to do time series prediction and so on. This is something that we're going to worry about a little bit less in this class. But what we're going to worry about more are things that fall into the cache register and turnstile operations. So cache register basically means, you observe some weighted sequence of instances, and since it's a cache register, always money comes in, you never give anything out, just like in a shop. And well, you basically, well, okay, now it's not quite true because you can get cash back, but effectively, this was coined before cashback was invented. So user activity, for instance, falls into that category quite nicely. You want to know how many unique users came to a certain web page at a certain time. That matters because if I know how many unique users I had there, I can come up with an estimate of how much money I can make out of them, how many ads I can show them. So advertisers care about this. And you could do the same thing for revenue, for clicks, and so on. Turnstile is a little bit different. It's basically, so I think Muthu Krishnan coined that term. basically think of, you know, a subway system where you can walk in through a turnstile, but you also walk out. And at some point, you just want to know how many people are in the room there. So it's a bit like the fact that, you know, there's an elevator and, you know, 10 people walk in and 11 people walk out. The mathematician sees it, is puzzled, walks inside and disappears. That's essentially the type of reasoning that you want to have, where you can actually have additions and subtractions, and in the end you just want to have the final count to see. So we're going to see sketches for all of this. So here's a few nice applications, and to my knowledge Google Analytics doesn't actually use sketches. May be wrong, but so this is, for instance, a Google Analytics extract from my homepage. By now it's probably going to go up a lot because I hope a lot of you will actually look at your homework and so on. But basically what you see here is there's this big spike, and that's just when we gave the tutorial at NIPS. So of course a lot of people afterwards want to download the slides. And so it tells me, things like how many people come here and then are really frustrated and go away again, how much time they spend on the site. Well, it's not very much, 2 minutes. And how many new visits. Well, I probably don't have that many fans who come back and, check my homepage, weekly for new papers or whatever. Which is all very reasonable. If you were to analyze this homepage with Quantcast, you would, for instance, find out that apparently, or at least supposedly, 90% of my viewers are Asians, which means that Quantcast's user definition algorithm is probably slightly broken. They probably correlate Asian with, well, nerdy, and so, okay, whatever. So the point is, you might actually want to build a system that can provide you with similar data, and without really having to use a lot of batch background processing. I want to have something that's very lightweight. And I'm going to show you how you can actually do this. On top of that, you want to get those estimates right now. Why would you care? Because if I say put some new content on my website, I want to know right now that the stuff is actually popular, that people are actually clicking on it. And right now you pay premium to get this. In some cases I have very simple things like a query stream, so that's over time. And so I just looked at a comparison between machine learning and data mining, and you can see usually data mining really beats out machine learning, even though that gap has been closing recently. And then you can look at which are the places where machine learning is much more important than data mining, and Berkeley, Stanford, Whistler, and so on. They're all up here. Interestingly, here Madison, Wisconsin has a very strong data mining group. Tells you something about why it's about tied here and why they actually request a lot. This is probably because it's coming from Yahoo. Google doesn't log their own data, so that's why Mountain View is not on that list. And yeah, CMU also prefers machine learning to data mining, but they apparently come less, search for it less.
So about signal thing, that's because of holiday?
So basically the blue bar is machine learning, the red one's data mining, and these are just the top cities.
I mean, you can see a seasonal effect on the volume.
Yeah.
Because of holiday, people don't search anymore?
Well, it may very well be that people who look for data mining don't really know what they're looking for, whereas if you're looking for machine learning, you have a pretty good idea. Now, what's actually happening is that data mining has gone mainstream as a keyword, and so a lot of people who don't necessarily ever, would ever venture into university to take a class in machine learning or data mining still might have heard of this. So you might, hear it on Fox News, but I doubt that you will hear machine learning on Fox News. So, what do you care about here? Well, you want to detect trends early. So, for instance, when Bin Laden gets killed, you want to pick that up very, very quickly such that you can then pay an editor to write a new story, post it on your homepage, and then you get more users, more viewers. So you basically want to be able to pick up on new and changing things very quickly. You want to find out what the most frequent visitors are. So if I know that, for instance, the Slashdot crowd is coming to my homepage, I might actually want to provide content specifically for them. Another example, network traffic analysis. So this is for some traffic analysis tool, and okay, it doesn't really matter what you're seeing here. Not that they actually explain very much on their homepage, except that you can produce pretty graphs. But what you actually do care about is, for instance, suppose I'm AT&T and I want to screw you out of a lot of money for your phone usage, then I'm going to throttle the top users. Or if you're using tethering and you don't use it that much, you're probably not going to run into trouble. But if you're one of those really heavy users for your iPhone, using a lot of data, well, these are the ones that you want to look at, and then maybe pay a human to actually look at the logs and decide whether I should, try, squeezing more money out of them, or disable their service, or send them a not so nice SMS. Maybe Verizon or Sprint do the same thing. I don't know. So you want to do some of this analytics also on machines with very limited footprint. So if you have, for instance, a network switch, these are usually not high memory machines. They optimize for something else. And so you might have only maybe a couple of 100 megabytes as footprint, maybe only a couple of megabytes. You want to find out, which are your busiest connections, maybe, your most frequent customers. And in many cases, you don't really have only one single spot where you gather that data. You get a lot of different places. Financial time series, I guess everybody knows that this is a time series, and so you do interesting predictions on it. And if you do really well, then you will stop publishing about it and get very rich. And if you don't do so well, then maybe somebody else will write about you. News, it's an interesting data stream as well. So what you may have is you get a news stream. You might actually want to be able to aggregate various articles into entire storylines. So depending on how we go, towards the end of this class, we might actually look at an algorithm which does a couple of fairly sophisticated tricks in order to thread together automatically fully unsupervised articles into individual storylines in a way that's actually better than a lot of humans would do. And this will then require a fair amount of Bayesian non-parametrics and sampling and distributed inference. So we'll basically, right now what we're doing is essentially a lot of warm-up to get to the algorithms that use all those tools to do really cool stuff. So this is why we have a very diverse bag of tools that we have to play with. Okay, so let's start with something very, very simple. Estimating moments. Sorry, yeah?
Yeah, just a question. What's the difference between a sketch and a stream?
Okay.
I've never heard sketches defined.
Okay, very good question. So data stream is the data that's coming in. Maybe, through some API, whatever. For instance, I might have the Twitter fire hose. That's a data stream. I mean, if you're paying for the Twitter fire hose, you'll probably dump it to disk and log it anyway, but it's a stream coming in. It's a data feed. A sketch is something that you're going to do to come up with a compressed, digest of the data stream, such that I can ask very quick questions to the sketch as opposed to the stream. With the stream I may not be able to replay, but the sketch I will be able to reinvestigate again. So, for instance, a simple sketch would be, the average. So in that case, all I would do is each instance that comes in, I add to, my counter. And I also have another counter which counts how many instances I've seen so far. And if somebody asks me, give me the average, I just divide those two numbers, and presto, here's an estimate of the average. I don't need the stream for that anymore. That can be completely gone. In some cases, the stream may also simply contain so much data that I can't log it all. So that's the key difference. Any other questions? But by the way, thanks for asking. Okay. So here's a simple warm-up exercise. So I have a stream of items, and I want to compute some statistics of what we've seen. And so, if I have a small cardinality in that set, well, that's really easy, right? Because, let's say I have maybe 100 distinct items, then, I just keep, that list of 100 items around, and each time I see an item, I increment its counter. So if I have n items, memory requirement is essentially order n times, log, basically, which, log total count, something like that, which basically determines how many bits I need for each counter. And the computation is actually fairly cheap, because I just need to do a dictionary lookup, and that's it. So, very simple problem if I have, a few million items. If I have really large cardinality and I don't maybe even know beforehand, then I can't really store the counts exactly anymore. That would require too much memory. And so I can't actually get exact tests for previous occurrences anymore. So I need an approximate data structure. And what this lecture is about is all about approximate data structures to answer interesting questions about the data stream. Okay, so here's... Yep.
So, and let's let you work like your dictionary in a tree with some nice data structure, you can work on like O log n complexity, right?
Yes, so you may do that.
For example, your shape. The shape is what you cannot code in like water, right?
Yes, but if I have only exact shape matches, then I can look it up, right? If I have approximate shape recognition, then basically, so this is all just for discrete data symbols on a data stream. If I have generic shapes, let's say I'm seeing 5 apples and 3 bananas, then I can't do anything. For shape matching, I may be able to get some invariance, but yeah, that's a more interesting research problem. I mean, I just drew the shapes to give you some idea of what I might see.
Okay.
But basically think of them as binary problems. So here's a simple problem for you guys. Suppose I have a sequence of n instances that I'm going to see, and one of them is going to be missing. I'm going to observe the instances in any arbitrary order. So I'm going to see n minus 1 instances, and I want to find which one is the one missing. And I want to do that with the smallest number of bits. How would I do it? The question is, I have n instances, one of them is missing, I observe all but one, find out which one's missing. Pretty good. That's exactly what it is. Yes. So the solution is exactly, you take the sum of all the instances, and you subtract as you see one after the other. And since the subtraction is commutative, it doesn't matter in which order you apply it. And so in the end, what you're left with is exactly the identity of the instance that I was missing. So I have to first, at some point, compute the sum. I can do that beforehand once. And now it's really easy. If I had, 10 machines which see a substream of the data, you just compute the sums on those subsets and subtract it from the total sum. You still get it. Question?
Yeah, so why don't you just from 1 in every time just increase and then compare? Is that data?
That's the same thing. Well, if I have, okay, so basically, whether I compute a minus sum over all, bi, I put the bracket here or I put it there, doesn't really matter, right? That's completely equivalent. Now, how many bits do I need to store this?
What is sum of items then?
So, well, I'm assuming they're all ordered at the moment from 1 to n, just to make my life easier. Do I really need, log n squared bits? So, maybe 2 log n bits. Do I need that many of them? Well, you could have XI, yes. But, so, I don't really need them. I only need to store the least significant bits. Sorry. Yeah. So I don't really need the leading bits. I can just truncate them off because I know it's going to work out fine in the end anyway, because somebody will tell me when I'm done with my data stream. And then my data structure in the end will really only, basically I only need to be able to encode the numbers between 1 and n. That's it. So, let's make our problem a little bit harder. So now up to k of them are missing. How can we find them?
if you don't mind about the storage, just like create a table, right, with the n, and then you just like make a Boolean variable, like indicate this variable you found it or not. You just need like n, o n.
Yes, but order n might be too large, right? So before that, we had an algorithm that worked in order log n time.
Okay.
So log n space. So can we do something that's order log n here as well? Exactly. You're good. Very good. Or you've seen my slides.
How you interview by that? That's the first one.
So, but yeah, that's exactly what you do. You basically store the piece moments here, and then you basically decrement all of them correspondingly. Then in the end, you're left with, you know, equations that look as follows. You basically have, let's say, sum over, you know, all the xi's. You have sum over all the xi squared in some set. So, and that allows you to work out what you're missing. Let's say, for instance, for two items, you have that a plus b equals c, and you have that a squared plus b squared equals d. So from that you can work out that a equals c minus b. You plug it in here and you get an equation in b. You can work out b from that. And will in general require that at some point you have to start solving polynomials, root finding on that. But other than that, it's so the computation may be non-trivial. Okay. So that's a very simple statistic where we can get highly non-trivial information, namely, you know, which of those k elements are we missing in essentially only log n space, because we need to, you know, store, you know, log n bits. Well, actually, it's going to be for k. It's going to, you know, something like k log n. K times k minus 1 over 2 log n. Yeah, you need more bits as you move on. But other than that, it's very straightforward. You may actually be able to get away with just k log n if you only need the least significant bits of those moments. But I'm not strong enough in number theory to tell you that right off the top of my head. Maybe somebody here can do it. Okay, now, that's kind of fun, but a little bit boring. Let's estimate something a little bit more interesting. Let's estimate moments. So you care about moments because they tell you a little bit how uneven your distribution is, and you care about that, for instance, if you want to optimize things for database joins, if you want to do load balancing on your machines, and you want to know how much slower your slowest reducer is going to be, all that kind of stuff. So I'm interested in this quantity here, fp, which is just n sub x to the p, sum over all instances, all different symbols that I see. So that's the number of times that I see the symbol x, and I raise it to the power of p, and I sum over all possible symbols that there are. So f0 is just the number of distinct items. Right? Because basically this is going to, you know, just be a sum over 1, and for all elements in the set of items that I'm seeing. Okay, I'm defining to be that 0 to the power of 0 is 0. So that's a slight abuse of notation. And everybody does that. Now, the other thing is f1, well, that's actually really trivial. That's just the total number of items. I don't really need to have a fancy sketch for that. f2 is something that tells me, you know, how unevenly distributed, how large the variance of those sketches is. So you need that, for instance, for database query plans. So what I'm going to show you today is this thing called the AMS sketch, the Alon Matthias Szegedy sketch. It's a paper that's about probably 12, 13 years old. There's actually going to be a reference in the slides for that, and they won the Gödel Prize for that paper. I'm going to make our life a little bit easier for the purpose of this lecture, insofar as I'm going to assume that we have ideal hash functions. In other words, that these hash functions generate numbers that behave like random variables. if you want to do the analysis in the proper hardcore form, where you only assume certain pairwise independence, do read the AMS paper. Some parts are not that much harder, but overall it would require quite a bit more time to explain it in detail. So we're going to make our life easy. And in practice, your hash functions are going to be probably nice enough anyway. So I'm going to show you the algorithm first. So the first thing that we need is we need to compute the hash, get the hash function, which has the following property. The probability that hash of x equals j should happen only with probability 2 to the minus j. And so you might ask, how can I design such a well-known obvious hash function? It's actually very straightforward. You take, a run-of-the-mill hash that you would compute for those symbols. So I'm not trying to do shape recognition here. These are just, some symbols that I'm seeing. And we compute a hash. I'm going to compute a hash with a binary string. And then I'm going to count how many bits are ones on the right-hand side. And actually, I should have 2 to the j plus 1 here. This has, no bits on the right-hand side. This has 2, and this has 4. So hash of the triangle would be 4, hash of the star would be 2, and hash of the diamond would be 0. Okay. I'm just going to count how many zeros we have. I could also just count how many zeros, in which case here this would be 1. I mean, it depends on how I put my counter offset, but I guess you get the idea. And then I'm going to look at the largest j that I'm going to see. And this is going to be my estimate for how many distinct items I have in my set. Sounds a bit crazy, right? So for each instance that I see, I compute this hash, count the number of bits that are ones on the right-hand side. If that number is larger than my current maximum, I'm going to increase it to that number. Otherwise, I'll just keep things. The first thing to think about is immediately it follows that if I see the same symbol twice, nothing changes. It's going to give me the same hash. So the same number of bits will be aligned. The second thing to see is, the probability that I get a sequence of 4 ones in a row is of course 2 to the minus 4. Okay, so this is also safe. So we have that property. Now we only need to show that things don't go wrong with high probability. So intuitively, you would expect this to happen, right? But the maximum of those hashes over my symbol stream is going to be close to log of the data set size, the number of distinct symbols. And the good thing is, of course, since I'm taking log of this, and if using binary storage, I only need log data stream size many bits to really store this. So this is quite crazy, right? So I need log many bits to come up with an estimate of how many distinct symbols I have. And the theorem is that with high probability, this inequality holds. That my estimate minus the log of the data set size is in absolute deviation that this exceeds log c, so some constant, is less equal than 2 over c. So we're going to prove that now. Yes?
Sorry, so you're asking for hash of star, and what's coming out as an integer represented in binary as 1 over 1, 1, okay.
Yes, and then I'm counting the number of non-zero bits to the right-hand side, and that's the hash that I'm going to use for that. So basically I compute an intermediate hash, and then I do something else with it. Okay. So let's first of all rewrite that equation here into something slightly less unwieldy. And the way to do this is by exponentiating the argument in the probability expansion here. Because that just means that log x is less equal than, here we have c times, well, basically max over j, hash of j. And it's less equal than 1 over c max j hash of. So that's basically the condition. So let's go and compute the upper bound. So this is basically here. Now let's say, well, since each of those j's, well, you know, occurs with probability 2 to the minus j, so for an individual instance to, you know, be larger than that, the probability is 2 to the minus j. And if I have, you know, x many of them, so there's no log here. I just have that data set size. And I want this to be less than j, less than c. So from that immediately it follows that j has to be, well, less than log c plus log x. And that exactly gives us the upper bound. And okay, I screwed up in the sense that here on the slide I have c being a number less than 1, and on the whiteboard I have c being a number larger than 1. That's about the only difference. But you can easily switch it. Okay. Good. So, right from, you see how you get the upper bound, right? This is the probability for a single instance to have, you know, a hash value larger than j. So I'm defining j, well, let's call it j hat here. This is j hat. Okay. Now, I want that probability is less than c, so I'm taking the union bound, because if this guarantee holds for a single symbol, and I have x many of them, then x times that probability is definitely an upper bound that nothing bad can happen overall. And then all I have to do is I just have to solve for j. So I get that 2 to the minus j is less equal than c over, you know, a number of distinct symbols, and then if I solve for j, I get my inequality. J hat. Now let's look at the lower bound. So the probability that I'm not exceeding the bound, it's basically, you know, 2 to the minus j is the probability that I'll see this guy. So 1 minus 2 to the minus j is definitely lower bound. Now I have x many of them, so basically x many of them would have to stay below that desired target. So raise that to the power of x. Now that you can simply see is, you know, less than e to the x times 2 to the minus j. That's a very useful inequality. Basically 1 plus x is less equal than e to the x. Right? That's what I'm using. Well, sorry, minus x is, we also have that property.
What? Plus x is also true,
Yeah. Right. Yes, but we're using the one for minus here. Anyway, so and there would be a minus here and somehow. Yeah. There's a typo on the slide, it's a minus. And then, well, you of course know this. Okay, you want this to be less equal than 1 over c, which you can bound accordingly. So then you solve for j and you get exactly that lower bound. Yep.
So C here is just any positive constant.
Correct. And
Where do they come from?
well, that's the confidence threshold that you want to pick. And so you can ask, I want to have, something that is true with very high probability. So then you would pick here, in this case, C to be maybe 100, maybe 1,000. Huh? And so if you pick C to be 1,000, then you will get an inaccuracy which is of the order of in terms of the score here, it's going to be log of 1,000. Now, how do you make it actually better? Well, you could, for instance, just invoke the sketch several times. And if you invoke it several times, then something that might fail, with probability 1/2, if you then take the median of some numbers, you will get actually a more accurate sketch. So I'm going to show you that exactly in a few slides from now, how you can use averaging and median or min operations in order to boost your probabilities. It's a fairly standard tool in computer science.
After you choose a C, you will choose the upper bound for the counter, right?
Yeah.
And so the base you need to start the counter is just log x plus C.
Well, in practice, you basically pick some number. I mean, you would probably pick, 64 or whatever, and log of something has to be I mean, you would have to have a really large number for, 32 or 64 bit to fail. Because, if you invert it, it's e to the x, right? So, compute e to the even 32. Well, okay, 2 to the 32, right? And, well, your computer could run for a very long time on that. In the original Flageolet-Martin paper, they didn't have this log x analysis. So what they actually did is they stored exactly those bit strings and just, started setting bits to 1 accordingly. Now, what you get through that is an interesting, phase transition that you will have essentially lots of 0 bits up here, and then at some point it basically transitions to all 1s. Basically, they only would set the largest of the bits from that sequence to 1, and the log comes from the fact that essentially you only need to really zoom in onto the region of where that transition happens rather than the entire statistic.
I think you have a small typo there.
Okay.
Maybe this is actually X, right?
That's what?
Max HX.
Yeah. Yes, of course. Yeah. Okay. So you could do interesting things like, for instance, you could have a counter which, you would just increment with, some probability, and with that you can, play with, if you don't like working with base 2, you can work with different bases. Another thing that's quite interesting is if you have a Bloom filter, you can actually squeeze one of those Flageolet-Martin counters into your Bloom filter rather than just a single bit. And that's one of those cases where you actually care about how large log n is. And yeah, the other part I already told you. Now, here's a slightly more interesting sketch, the F2 sketch. So the strategy is basically, we want to get, the sum of the squares of those random variables. And so the AMS paper has a very sophisticated construction with essentially a clever binary code that has certain independence properties. I'm just going to use ideal hash functions because it makes the analysis so much simpler. So the strategy is basically as follows, and that's this is the general strategy that we're going to use over and over again. I design some random variable which has the right property in terms of the fact that the expected value of it is what we want to get. Then I pick a of those random variables and I take the average over there. That means that it reduces my variance. So it'll be already naturally more concentrated. And then I take a couple of those instantiations and take their median. And this will make sure that, you know, outliers don't screw up things too badly. Because otherwise, you know, what's wrong with just taking an average over all those random variables rather than taking averages over subsets and then taking their median. The median is essentially the procedure that makes it robust to things, bad things happening at your tails. Okay. The random variable that we're going to do in this case, is a Rademacher hash. So I don't know whether that's a proper name for it, but there is this thing called Rademacher random variables, which you may or may not have encountered in essentially, you know, uniform convergence theory, computational learning theory. And these are random variables which take on values 1 or -1, and you have a lot of them and they're all independent. Now, what I'm going to do is I'm going to use a hash equivalent of that. So these are, again, variables that are 1 or -1, except that I can recall their value at any time if I should want to do so. So it's like a Rademacher random variable, except that I don't need the storage. And so for each instance in the stream, I'm going to compute the corresponding Rademacher hash, which depends, of course, on the symbol, and, you know, 2 additional parameters I and j, which is going to give me the ijth random variable x here. Now, what you can immediately see is if I see the same x twice, you know, it's going to have the same sign. So what I'm going to get in the end is, well, nx times the sigma thing. Okay, I'll just write it out in more detail. So the sum over all symbols x in the stream of sigma of I, j, and x can also be written, of course, as the sum over all x in my data set. And now I basically count how many times I get the same x. Okay, so I have n sub x times sigma I, j, and x. Right? And this is what I'm going to call, well, at least a proxy for what will become my random variable. So I'm going to call it theta ij. Now I'm going to take the square of this and its expectation. So ij squared is, of course, you know, the sum over all x in the set in x squared. That's good. That's what I want. However, I'm also going to get the sum over all x not equal to x prime in x prime sigma I j x sigma I j x prime. Now if I take expectations, then okay, this doesn't really over sigma. This doesn't really depend on sigma. This doesn't depend on sigma. This, however, does. Now if I have an expectation over those hashes, see, they have a different argument here. So this just goes away. And I get exactly what I want, namely F2. That's the slide. So now I have an estimator for F2. But it has very high variance. And what I need to do is I need to reduce the variance and need to get sufficiently high confidence that what I'm doing is right. So I'm going to call this the average median theorem. I don't think it has a proper name, but it's a very useful tool, so I'm going to just pull it out as a proper theorem. It's essentially a very useful proof technique. So I take random variables xi, j with mean mu and variance sigma, and I have a mean estimate x bar, and then I take the median of it. And the probability of deviation by more than epsilon is bounded by delta, so that's exactly what they want, small deviation from the true mean with sufficiently small probability. If I go and take an average over A equals 8 sigma squared over epsilon squared many instances, and I do that B many times, namely 8 over 3 log 1 over delta many times. So I need A times B many of those instances. And then I will have an estimate of the mean that is actually good.
So this estimate has a smaller variance than just directly taking the mean?
Well, in some cases you're right. In many cases you aren't. Okay, so here's one of the cases where, so in the limit everything's fine. So central limit theorem will kick in, and somehow when you read this algorithm, it feels wrong, right? Because you're actually not really using all the data. You're taking the median and you're throwing away a lot of things on the left and right hand side. So it feels like really the wrong thing to do. Unfortunately, or fortunately, it isn't, because so you could have random variables which with small probability might have really large deviations, and that's what the median protects you against. So maybe you can get slightly higher statistical efficiency if you use a trimmed mean estimate rather than a median. You basically throw the 10 largest and 10 smallest guys away and take the rest. So that may very well work better in practice. So in other words, if I had to code this up and make money with it, that's probably what I would do. But for the purpose of this proof, okay, I'll show you how you get essentially this bound. Now there's a small footnote that these guys here claim a slightly smaller constant. They claim 2 rather than 8 over 3. I was unable to get that constant, and I think it's just a small bug in their reasoning. So I'll walk you through the proof. Let me basically just say, well, it's Chernoff bounds. Okay, now, the first thing is you just use Chebyshev. Because what we know is that if we, pick many of these guys, then by Chebyshev, the probability of deviation is going to be less than 1 over 8. So that's reasonably well controlled. Right? So remember how Chebyshev went? It was basically, variance divided by the confidence range, and we just picked our confidence range such that for this epsilon everything works out. So this gives us a reasonably small, but still troublingly large probability that something bad could happen to you. Right? So it's troublingly large because 1 over 8 is not something you would really want to bet lots of money on. So what you now need to do is you need to boost that probability. So we have all those independent draws of a random variable with 7/8 probability is going to be fine. So we have all those draws. Now we know that 7/8 with the 7/8 quantile things are good. Now you need to make sure that if you take the median, you need to make sure that at least half of the instances in your data set are well behaved. If at least half of them are well behaved, you're fine. You need half plus 1. So this is, by the way, also the same reasoning as what was the case in the sloppy quorum for the distributed key value storage 2 weeks ago when we talked about Amazon. It's the same reasoning here. You need to make sure that the majority doesn't get corrupted. Now, therefore, what you need to show is that for your empirical average, you have a true probability which is 7/8, you need to make sure that the empirical average is more than 1/2. And that's a classical application of a Chernoff bound. And the tightest that I found for that type of inequality is the Mitzenmacher and Upfall version of the bound. And so it basically goes that, you know, the probability x is greater or equal than 1 plus delta mu is less equal than e to the minus mu delta squared over 3. And then you just plug in, you know, epsilon equals 3, mu equals b over 8, and then you have the inequality. So this is very straightforward.